right. Yesterday we talked about the first of three people that we're going to talk about that came after Niels Bohr. So Niels Bohr came up with this model of a hydrogen atom. It worked really nice. When we say it worked, we mean that his equations he came up with, from those equations he was able to calculate the wavelength of the visible photons that we see in the bright line spectrum. So that bright line spectrum has been known about for a long time before him. They knew what the wavelengths of light coming out of these glowing samples of hydrogen were. He was able to come up with a set of equations that the answers were match those numbers. Okay? When he tried the same math for helium, it didn't work. Okay? So he knew there was something missing or something being done wrong or something. Okay? So there are a couple of things that are going to change over the years following Niels Bohr. First thing was Louis de Broglie comes along and says Einstein had the idea of waves or particles. De Broglie flips that around and says if that's true, then surely particles can be waves. Okay, but you can't just say something like that. You got to try to prove it. So he does a bunch of math, and it all boils down to a fairly simple equation that allows us to calculate the wavelength of a particle, okay, which doesn't make any sense to us, okay, because when we view objects moving about, we don't see them waving, right? We don't see them as having wavelength and frequency and amplitude, okay? We did some math on that yesterday, and what we found, and we talked about orders of magnitude, right? Talked about that, okay? So what we found was that a person, myself, walking around the room, has a wavelength that's 36 orders of magnitude smaller than me, okay? Which means it is completely insignificant, right? Not only is it undetectable, it completely doesn't matter, okay? Except for the fun of the conversation of saying that it's not zero, so therefore when you're walking around, you are a wave, okay? But that's just really for fun, okay? Because there's no practical application of that. There's not even a machine or device that can even pick up on it, okay? But as you get smaller and faster, it might become more important. So we did it with a baseball, which is much smaller than a person and can be moving much faster than a person. And we're still 32 orders of magnitude smaller than the baseball. Okay, so it's still very insignificant. Okay, so when you throw a baseball, the wavelength of that baseball is irrelevant to the motion of that baseball. Okay, so no need to think about it, no need to worry about it, no need to do math with it. Just it's nothing. Okay, but it's technically not nothing. So just for the sake of conversation. But when you get down to the electron inside a hydrogen atom, okay, now it becomes not just significant, but it becomes very apparent that there's an issue here. Okay, the wavelength of an electron, though still a tiny number from when we think about the size of numbers, okay, 10 to the negative 10, is 5 orders of magnitude larger than the electron itself. Okay, so now we've got something that's significant, okay, and very important to the movement and motion of this electron. It's also about 3 times larger than the hydrogen atom itself. Okay, that would be equivalent to me walking around the room, my wavelength being 3 times the size of this room. Okay, so 3 times my size at least, right? So anyway, that's very, very big deal. What that means is that from Rutherford forward, so let's remember Rutherford found the nucleus and said the electrons were somewhere outside that, right? They knew that the immediate question to answer next was, where were the electrons and how were they staying out there? Okay, why didn't they collapse, right? Okay, part, choice B might be why don't they fly away, but the first question is why don't they collapse, okay? So why is the universe more than some fraction of a nanosecond in existence, right? Why didn't it just be and go away just like that? There's some reason for that. There's some way that these electrons are staying where they are. So Rutherford was looking for that, couldn't figure it out. Bohr thought he figured it out, had problems with it. Okay. What de Broglie adds to the conversation is that don't treat it like a particle. All of Bohr's equations were the same as planets around the sun physics equations. That's treating it like an object, like a particle. He said, don't do that, treat it like a wave. Okay? So that helped with the situation. It doesn't fix it all the way, but it helped. And that brings us to a couple of pictures on the next two slides here. There we go. Okay, so anybody play guitar? Anybody? Anybody know anybody plays guitar? Anybody play any other kind of stringed instrument?
Yeah, I play the violin.
You play the violin?
Yeah.
Okay, it works pretty much the same way. Okay. So, stringed instrument, all right, if we had a guitar up here, a stringed instrument works because first off, you tune it, right? You adjust the stiffness of that string. So that when you pluck the string, you get a vibration, right? That vibration is supposed to set up a standing wave in between the ends where the string is attached, okay? That standing wave, if everything's adjusted correctly, will have a wavelength that's equivalent to a sound wave of a note, okay? In other words, the human brain hears it and goes, yeah, that sounds nice, okay? There's a lot of other frequencies and wavelengths that you can produce on an instrument that the human brain goes, oh, that didn't sound good, right? That would be like if I was playing a guitar, it would probably sound like that, okay? If you want to change it, okay, you want to change the sound of a stringed instrument, you change the length of the string on a guitar by pressing the string against the fretboard, right? And every time a guitar player moves their hand up and down the fretboard, they're changing the lengths of the strings, okay? Which changes the wavelengths that can exist on that string, which changes the sound. If they're doing it correctly, they go from one note to another note. If their finger hits kind of in the middle of two places, it won't sound exactly right. Okay? It won't be an actual note. It'll be some other frequency that doesn't really make music, as we call it, right? All right, so in other words, there's certain standing waves that can exist on an stringed instrument that make allowed, I like to use quantum mechanical terms, make allowed frequencies, okay? And there are a bunch of not allowed frequencies, okay? Meaning, in music terms, we don't like the way it sounds. In quantum mechanical terms, it means they don't exist at all, like they are non-existent things, okay? So, why do the electrons, why are they able to stay in those 1 of 7 orbits? Because their wavelength matches that space. So they wave around, instead of going around in a circle, they're going around in a wave. And the wavelength matches the circumference of that orbit, okay? And that way they just keep on waving around. If the wavelength doesn't match the space, it's not allowed, okay? It's not that it sounds bad or looks bad. In terms of electrons, it just can't be at all, okay? So it's got to have a wavelength that matches that energy level. All right? Instead of going around in a circle, it's waving around in a space. All right, more of a region of space instead of a line or a curve. Take us to the next slide here. Okay. So if it's an allowed orbit, then it just waves and ends up right back where it started, just keeps on waving, and just keeps on going and keeps on going, like the picture on the left right there. If it's not allowed or forbidden, it says here, okay, then it's going to do one of two things. It's going to wave around and end up flying away, or it's going to wave around and end up collapsing into the nucleus, one or the other, depending on how off it is, okay? But there's basically an infinite number of positions in which the wave would either fly away or collapse. And there's 7 positions which it worked perfectly. So that's the 7 orbits, 7 energy levels that it's allowed to have. Okay. Everybody kind of follow that idea? Okay. So I thought they were on to something there. Everybody's getting happy. Everybody's thinking we're going to figure this out. We're going to end up with this nice, neat little equation. It's going to allow us to predict where electrons, know where electrons are, which the big thing that is then you can predict where they're going to be. All right, and you can predict all kind of behaviors and stuff. It's going to be so great. Until 1923 or so, thereabouts, somewhere in the 1920s, the Nazis mess it up. Not really. He wasn't a Nazi yet, but he ends up being one. Werner Heisenberg comes along, and this is really interesting, okay? Werner Heisenberg comes along and says, we don't know anything. That actually finding the electron would cause you to lose it. Think about that statement for a second. That should make complete sense. Finding something makes you lose it. Okay, if I look back here. The Nazi comment, we talked about that yesterday, about Heisenberg. We mentioned him. We talked about von Braun, didn't we? And how bad he was. But Heisenberg ended up being later on, probably 15 years after this, maybe thereabouts, he ended up being the head of Adolf Hitler's nuclear weapons program. Okay? So that makes him not a nice guy, because he's trying to build highly destructive weapons for a guy who didn't have a problem with indiscriminately murdering folks. Okay? So you can only imagine it's hard to imagine what Adolf Hitler would have done with access to such as that. Okay? Probably just killed everybody. If you weren't blonde hair, blue eyed, you took a nuke to the face, probably. So bad deal. We got like 2 people in here that might make it. Okay. The rest of us would have been vaporized, or our grandparents, great grandparents would have been vaporized somewhere in the 1940s. Had Heisenberg been as smart as he wanted to be. But anyway.
RP on the black folks, man. So RP on the black folks. In this hypothetical situation.
Y'all probably would have went first, you know?
Yeah.
Just saying.
We're the farthest thing away from.
Yeah, he probably would have started on that end and worked his way back.
Yeah.
Honestly.
Dark as you can.
Yeah, I mean, just test subjects, you know. I mean, that guy was, that's just the way he was. Not good, but it's true. That's the way he was. So, anyway, that's what Heisenberg ended up doing later. Before all that, he was a world-renowned physicist who came up with the uncertainty principle. Okay, so let's talk about this a minute. Look around at the person sitting next to you. Do you see them?
Yes.
Okay. Are they there?
Yes.
You sure?
Yep.
100% positive that.
1,000%.
I'm not sure.
positive.
I've learned to not trust things.
That's a good thing to do. Okay, here we go. Let's see. Who's got on a color? I see. All right, Paul, we'll go with the jersey over there. You got a blue shirt on, right?
Yep.
Okay.
I have a blue shirt on under it if you want to take off.
No, you were good. Offensive linemen should keep their shirts on.
I'm good.
Okay. All right. So, how do I know you have on a blue shirt?
You have eyes.
Okay. What's the physics behind how I know you have on a blue shirt? Do I have photons? Okay. So photons are coming from sunlight or these mercury gas filled bulbs here, right? Whole bunch of photons. That's white light, right? So mercury, when it glows, it produces white light. Okay, we got all kinds of photons there. So photons are hitting your shirt, all right?
Right.
Your shirt has been soaked in organic compounds that absorb all the photons except blue ones. Okay. All right. So let's go real basic here for a minute. Let's just pretend that's cotton. I don't know if it's probably not. Okay. But what color is cotton?
White.
White, right? So cotton is white. Okay. So if you have on colored cotton clothing, they dyed it, right? They soaked the cotton in something else, and that something absorbs photons except the color that we see. So whatever they soak that shirt in, it's absorbing all the photons except the blue ones. Okay? So everybody's being absorbed, it's coming out of light except the blue ones. The blue ones are bouncing off the shirt, okay? And they're coming in and hitting me in the eye, right? And they're refracting through my corrective lens, because I wear glasses, and then they're refracting again through my slightly messed up regular lens, okay? And they're focused on the back of my eye. They cause a chemical reaction that sends a signal to my brain and says, kid sitting in a desk with a blue shirt on. Follow that? Okay? And that happens trillions of times per second. Because there are trillions of photons flying around this room,
So,
and they hit me in the eye all the time. And my brain comprehends that as blue shirt, orange shirt, plaid shirt, whatever.
so what about colorblind people?
Colorblind people have a chemical problem in the back of their eye in which the wrong chemical reaction. Most people who are colorblind have a green-red mix-up, which means it's generating either the wrong chemical reaction or the wrong nervous signal, and your brain is crossed up. When it comes to red photons and green photons, it's not working right. If you're truly colorblind, which is extremely rare, in other words, you see everything in just gray, that means that none of those color reactions are functioning. And therefore, you're registered, your brain knows there's objects there, but it's not seeing colors.
Gosh, that sounds awful.
And how does the frequency tie into it with the colors?
Because that's your different energies and wavelengths. So the different energy of the electron is causing the different chemical reaction. It's triggering some kind of chemical reaction based off the energy of the photon. So it sends a corresponding signal to your brain that says red, orange, green, blue, whatever, or mixtures, right? So we have all kind of, that's not like rainbow blue, that's some other shade of blue, okay? So that's some mixture of bluish and maybe purple, whatever photons that make it that color blue, right? So like the orange shirt, that's pretty much like the rainbow orange. So that's pretty much just straight up orange, probably not mixed with much. That color blue is sending off blue and some other things that make it a little, the different shades of blue, right? So anyway, point being though, photons have to hit it, bounce off of it, and hit me in the eye for me to observe that ball is sitting there with a blue shirt on, right?
So,
Now, go ahead.
so if there's no light, right? So there's no photons in this room. That's
Then it's dark,
you can't see. Okay.
right? We call it dark. There's no such thing as dark, it's the absence of light.
Okay.
There's also no such thing as cold. Cold is the absence of heat. Dark is the absence of light. Okay?
First week.
Is dark real?
Dark is not real. Dark is the absence of something else. Dark is there are no photons. Those black drapes right there are absorbing all the photons of visible light. So I see black.
So is there
Your
like
the white trim, the white piece of paper is on a white shirt. She's got a white shirt. That shirt is reflecting all the photons, the visible photons. So my brain interprets that as white. It's sending a whole bunch of chemical signals, and my brain goes white. Right? If I'm not getting any color chemical signals into my brain when I look at those drapes right there, my brain says that's black because there's no colored photons coming out of it. Right? I see it, but I'm not getting color interpretations out of it because it's absorbing all those things. Now, so for me to see something, here's where we got to focus here a minute, okay? Because we're about to get really imaginary, all right? For me to see Braden sitting in that chair, photons have to hit him and come to me. I have no idea which direction the photons came from. There's no way my brain can ever have any knowledge of which way the photons came before they bounced off. All I know is they came from that direction, right? There's an infinite number of directions they could have come before that. So I can't trace that backward, right? My brain has no information to do that with. It just knows that there's a bunch of blue photons coming from right over there. That's all it's got, okay? Now, two things, maybe they did, maybe they didn't happen. When the photons hit him, did they move him? Does anybody feel photons hitting you right now?
Yes.
Are they hitting you in a way that makes you bounce around?
Yes.
Feel the photons.
Yes.
Do not feel the photons. Unless you go outside in like the sunlight, you feel that, okay? But it's not going to bump you around, it's just going to warm you up, right? And that's really from the absorption of those photons, and it makes your molecules start vibrating a little bit. You get hot, now the sun's hot, right? You might like to sit in the shade, okay? Now, but it's not moving you around. So if I walk out in the sunlight, when the sun goes behind a cloud and it pops back out, right? I don't go, oh crap, like I'm getting beat up, right? Right? Okay, so
I feel like.
now, so the photons aren't moving you from that location, right? How long does it take those photons? Oh, this says talking time. Come to it. How long does it take the photon to get from your blue shirt to my eye?
Instantaneous.
Almost instantaneous. They're traveling, you should know this number, right? 300 million meters per second. You're about 4 or 5 meters away, okay? So if a photon can go 300 million meters in 1 second, it's taking it a nanosecond or less to get to meet you, right? Is there any way that he moved in the time it took that photon to get from him to me? No.
No.
Probably not, right? So when my brain says Ray Ball's sitting in his desk with a blue shirt on, it's probably correct, right? Because he's probably not been knocked over by those photons. He probably has not been able to move in the time it took photon to get from him to me. Okay? Question.
Okay, so you brought up the sun, right? So I was talking with Sarah, and I was like, when it's really hot, sometimes you like see the heat waves.
Yeah.
Is that the wavelengths of photons?
No, that's refraction of light because of the different densities of the air. So what you're seeing is because of the heating from the ground up, right? The reflection of the sun causing the air to heat. That the air is different temperatures, and therefore it's different densities, and therefore it's refracting light differently, so it looks wavy. It blurs everything. So,
This next summer is supposed to be the 17th year cicada hatch, and I'm like not gonna go outside.
all right, now here we go. Now we're going to take this whole conversation of photons, of me seeing something because a photon hits it, and it may be moving it, or maybe the electron, or maybe the object moved before the photon got to my eye. That whole conversation, we're going to take this down now to the atomic level. Okay, so now this is still my photon. Okay, now this is an electron. Okay, so here comes our imagination, right? This is an electron. It's sitting right there, minding its own business. Okay, all right. If I'm Rutherford or Einstein or Planck or Bohr or Broglie or whoever, and I'm trying to find that electron, what has to happen? If I'm trying to find Ray Ball sitting at his desk, I have to look at him, right? Which means we have to have photon interaction with the object I'm looking at and my eye, or I won't find him, correct? Okay, so if I want to find this electron, I've got to see it, or at least use some type of detection device that can pick up on the photon. Let's just say the photon that will interact with that electron is outside the visible range. We got other things that can, quote, see that, right? But got to have an interaction with a photon to know it's there. So here comes my photon, right? You could be coming from an infinite number of directions, right? It hits the electron, it hits me in the eye, okay? What does my brain say?
You just got hit in the face.
My brain says I have there's an electron where?
Right there.
Right there. Is it? No. Do I have any way of knowing where it went?
No.
No. Okay. So the act of finding it makes me lose it permanently. Okay. So because since there's an infinite number of ways this could have come in to hit that electron, that means there's an infinite number of places it could now be, save one spot. and that's where it was. That's the one place I know that it's not, but there's an infinity minus one possible places that it now could be. The only thing I know is that it's not there. Right?
So we can't be like beat up by the photons, but the electrons.
Electrons are, because they're on the same scale with each other. So photons and electrons bounce off each other just about like pool balls do. It's called the Compton effect. So like in regular old simple physics class, we do collision problems with tennis balls, pool balls, train cars, all kind of stuff bouncing off each other, elastic, inelastic collisions, fairly simple math, okay? You can do the same thing with a photon and electron. You have to change it just a little bit harder math than high school, but not really that much. As far as modern physics goes, it's pretty simple. It's called the Compton effect, where photon and electron will bounce off each other, basically like these two tennis balls would.
Why is it called the Compton effect?
Because Mr. Compton figured it out.
Who's Mr. Compton?
Some really smart guy, probably in Europe, probably a long time ago. I don't know. He may have been from America. I don't know. Doesn't sound German, at least, Compton, but maybe he will. I can't remember. Have to look that up. All right, so photon comes in, hits electron, hits my eye. Brain says electron there, automatically wrong, right? The right answer is automatically unknowable. Okay, so that's the Heisenberg uncertainty principle. Okay, now there's a mathematical doings of this too, which is pretty complicated. The final answer to it though is not too bad. We'll walk up here and talk about that. The main idea though is that was important to these people looking for the electron was it seriously busted their bubble, because he mathematically proved that you're looking for something, right? You're looking for this electron. If you find it, then you automatically have lost it. So the only result from that could be is we got to quit looking for it, because there's no point in looking for it now. Because if we were somehow to find it, then we made ourselves know nothing about it. Like that gain of information is actually a complete loss of knowledge, which is a pretty deep thought. Think about it, right? But that's the situation they were in. Okay, so we had this little mathematical deal going here. Okay, you don't have to do math with this. Okay, this is the uncertainty in an object's position, and the uncertainty in its momentum, which is basically its velocity. Those two things are always greater than or equal to Planck's constant divided by 2 pi. So here comes Planck's constant again, just flying out of nowhere into some equation. Okay, because as we said earlier, Planck's constant turns out to be basically the fundamental thing about the whole way the universe works. Okay, pi shows up in random, what seems like random places too, but that has a lot to do with symmetry. Circles are symmetrical, right? So pi just shows up in all this three-dimensional symmetrical stuff. Okay. Yep.
The guy who made the Compton effect, his name's Arthur Compton.
Okay.
And
Where was he from?
He was born in Wooster, Ohio.
Okay, so he's American. What year was it?
Huh?
What year did he come up with this effect?
He won a Nobel Peace Prize in Physics in 1927.
He won the Nobel Prize in Physics.
Yes, in physics.
And which year?
Nobel Prize in Physics, yeah. Oh, yeah, he discovered it in 1927.
1927?
Yes.
Okay. So we had a little science going on in America in 1927. Go us, huh?
Yeah.
We weren't all just cold and corn or whatever. Okay. Good deal. So did he get the Nobel Prize in the 50s? You ever said?
27. What,
He
27?
discovered it in 27. When did he get the Nobel Prize?
27.
Oh, okay.
Or it says he was awarded the Nobel Prize in Physics 1927 for his discovery of the phenomenon named after the Compton.
Okay, so he discovered it prior to 1927.
Yeah, probably.
It's usually a few years before you get awards for stuff.
Yeah, it doesn't.
Doesn't tell when.
Yeah.
That's fine. Cool. So he was American. We do have some Americans prior to the war that did something. That's good. Good for them.
Oh, it was in 1922. He published
22. Okay.
his experimental theoretical results.
All right. Good deal. Good deal. All right. So
No,
real quick statement here. If you were doing the math with this, what you find is that if you know exactly where an object is, you have no idea how fast it's going. And if you know exactly how fast it's going, you have no idea where it is. So to know anything makes you know nothing, right? If you want to keep this reasonable, there has to be some amount of uncertainty in both of these, okay? So there's always some amount of uncertainty in any position and velocity measurement. Now, if we calculated that for Braden sitting in that chair, we're going to get numbers for answers that are like 20 or 30 orders of magnitude smaller than Planck's constant. Like, it's ridiculous, okay, how small the uncertainty is in that he's sitting there. So for all practical purposes, he's sitting there, right? But again, you take this down to the atomic level and it's a big deal, okay? Now, we're going to hide a cat in the box. And I meant to bring a cat, and I forgot.
I don't have that.
1926, a guy named Erwin Schrodinger put his cat in a box, okay? You've ever heard of this before? Okay. This is pretty interesting, all right? Now my tennis ball, so here comes our imagination again. My tennis ball is now a cat, okay? Because I did not bring an actual cat, even though I had one I should have. Here we have a box, okay? Here we have a box. There's nothing in the box.
It's gonna suffocate.
Is it magic trick?
But is that
It's
actually?
not a magic. Huh? It's actually a box, best we can tell. Here's my cat, okay? This cat's alive. This cat seems perfectly healthy. Okay? I'm gonna put the cat in the box. Close the lid.
Suffocate the cat.
All right. Well, yeah, there's an air hole. You can suck it in.
There's no arrow.
Now,
I see.
now, is the cat still alive?
Yeah.
What would you say?
Probably.
Probably. That's the key word. Probably, right? Okay. But how do we know it's still alive? It makes noise, so we would have to hear it, right? Okay. But maybe it just like fell over when it died. We heard that, right? So to be sure that it's still alive, what we're gonna have to do?
Open the box.
Open the box. Look at
Shake
it,
the
right?
box
Or
around.
shake it.
So right now, it's in the box. I can't see it, right? So I don't know if it's dead or alive. It is probably alive, okay? But it's not 100%. All right? So that's Schrodinger's little thought experiment about his cat, okay? So, point being, the electron in an atom is probably there, okay? It's got to be there to some extent of probability, okay? Because we know atoms exist and chemical reactions exist and all these things happen, right? There's protons and there's electrons and there's got to be some kind of order to this thing, right? So the electrons are probably where we think they are, all right? But we can never know that for sure. Just like my cat is probably alive, but the only way I can know it is to open the box and look at it. Well, if I open the atom and look at the electron, according to Heisenberg, I'll lose it, right? So the best thing we can do with the atom is don't look at it and just go with the probably it's there. Don't look at it because you'll mess up. You look at it, right? It'll make it go away. So as long as it's there, don't observe it. Just assume that it's probably what we think it is. So he takes this idea, okay, and comes up with what we call the quantum mechanical model of the atom. And this is still the model that we're going with. We're 97 years later, okay? This is what we got. And we got a couple little cartoons to look at first, okay? So, wanted, dead, what does it say? Dead and alive. So think about it now, your mind fixed to be blown, okay? All right?
Yeah, the cat is in the box.
So he took that thought experiment, okay, and then he started doing math with it. All right. Here's what the quantum mechanical equations say for the cat. And this math is way past high school. This is graduate school stuff. Okay.
I feel bad for the cat.
But the cat's fine, maybe, probably fine. Cat's probably fine. Okay, but everybody listen to this, because this will mess with your head a little bit. The question is not, is the cat dead or alive? The cat is both dead and alive, quantum mechanically speaking.
Right,
Okay?
because we don't know.
Because that's the two possibilities, right?
Right.
There's only two possibilities. It's dead or alive. That's the two possibilities. And in the quantum mechanical world, it's not an if or, it's a if and. That it's dead and alive until we can observe one or the other and then basically declare the other one false. Okay? All right. So his cat is not wanted dead or alive, it's wanted dead and alive. Okay? Because it's both at the same time. So those paradoxes, right? So go back to wave-particle duality, right? Waves are both waves and particles, not or particles, but and particles. And particles are both particle and waves, not or waves. Okay. Next joke. Schrodinger's cat walks into a bar and doesn't walk into a bar.
Whoa.
All right. So it's going in and out, not or out. Okay. So in our world of macroscopic, what we call Newtonian physics, people are walking to the right or the left, correct? I'll throw a ball up or down. In the quantum mechanical world, you're going right and left, up and down. Okay? So throw that into your little shadow boxing game and see how that works. If you're doing how you do that, all right? All right. Last one. Mr. Smart Cat. Okay? So what's different about that cat versus the cat in the box? I can see that cat. Okay? So we can eliminate one of the options of the dead and go with live. Okay? So I can see it and I can observe it. Okay? All right. Smart cat. Stay in a clear container. All right. Last thing for today. Last thing for today. What was the same and what's different? So we took Niels Bohr model and now we've adapted it, okay? And now we're calling it the quantum mechanical model, thanks to de Broglie's making it a wave. Heisenberg said, quit looking for it because if you find it, you're going to lose it. Schrodinger gets into this whole concept of probability. Here's what's the same. We still got 7 energy levels. That was correct. There's still 7 energy levels, okay? 1, 2, 3, 4, 5, 6, 7. Electrons transition, that's still a thing. They get excited and then they relax, okay? So we have excitations and relaxations. The relaxations produce photons, okay? That's what Niels Bohr said, and that's still correct. That's still part of our atomic model.
You said relaxations?
Produce photons. So the first 3 points right there are the parts of the Bohr model that we still have part of the atomic model today. The last 3 are different, okay? The last 3, Schrodinger says, treat the electron as a wave. Niels Bohr treated it like an object, like a particle, okay? Treat it like a wave. Not to get way, way above high school math here, but Schrodinger model assigns everything a wave function, which is an equation for the wave of the object. The square of the wave function gives you the probability of where it's at, and the energy and all this other stuff, okay? All right, so everything gets an equation, a wave function. We don't have to deal with wave functions. You're 4 or 5 years and about 5 calculus classes away from dealing with wave functions. Okay. All right. Exact location and speed are not needed in the quantum mechanical model. And that's a good thing because Heisenberg said can't do that anyway. So they developed a model that doesn't require knowing anything about location or speed. It's all based on probability. And it's a 90% probability, which people get kind of bothered by that. Why can't it be 100? Well, because Heisenberg said so, right? But 90% probability is pretty good. I would go to Vegas on 90% chance, right? I would buy a lottery ticket on that. I would buy on a 90% chance. I would buy a lot of lottery tickets. I would play a lot of slot machines if somebody told me there was a 90% chance. If you go to Vegas, your chance of winning is way less than 90, right? It's way less than 50 because the house always wins, right?
Have you been to Vegas?
I have not. Going in a couple. It's on our list of travel.
My parents got married in Vegas.
Really?
Yeah.
Ooh.
Yeah, it's today's their anniversary.
How about that? Thanks, Bill. Yeah. All right, so. Oh.
Oh, that's a good.
Oh!
All right, so real quick before the bell rings. All right, next week we're gonna get into the quantum mechanical model of the atom. We're gonna talk about what we can know about electrons, which is their energy level, the type of region of probability that they're in, the orientation of that region of probability, and which way the electron is spinning. We'll talk about all that next week. Got it? Good. Don't come to school Monday. We'll be closed.
Mr. Kittle,
Yeah.
I'm not gonna be here Tuesday.
Me
We
neither.
have a YLCC.
That's a shame.
I know